Let's move on to the power supply, which distributes power throughout the computer. In here, the main transformer reduces the voltage and bridges the isolation boundary between the primary side high voltage and the secondary side lower voltages used throughout your computer. Here's the control PCB that ensures a stable output voltage and sends adjustment signals to the switching power transistor on the primary side using opto-isolators. There are dozens of other components used to filter the input voltage and generate various output voltages, which are then sent to all the different hardware in your computer. For example, an SSD consumes just a few watts, and the connector uses these voltages, whereas your GPU can consume hundreds of watts using these connectors and these voltages. Next, we'll explore the GPU, but before that, let's take a step back and consider the technology we've covered thus far. Alone, each of these components doesn't do much at all, but when united, they combine to form a powerful system. Let's get back to dissecting this computer and move on to the graphics card and GPU, which is also the brain of the computer. Well, actually, this analogy doesn't really work very well, but anyway. Opening the graphics card, we see another PCB with the GPU's integrated circuit in the center, VRAM chips all around, and the voltage regulator module on the side. Above the IC is a heatsink with a fan to dissipate heat, and on the side of the graphics card are HDMI and display ports, a PCIe interface, and then on the other side is the input power connector. Let's focus on the GPU integrated circuit, which, similar to the CPU, has more than 1,000 solder pads that connected to the PCB. Opening the packaging, we find the GPU die, which is noticeably different from the CPU. In here are approximately 11.8 billion transistors organized into 6 graphics processing clusters, totaling 28 streaming multiprocessors. Each streaming multiprocessor is composed of 128 cores, resulting in a total of 3,584 cores. Each core has sections for integer and floating point arithmetic, and sections for queuing in the operands and collecting the results, and is far simpler than a CPU core. Additionally, on the die is an L2 memory cache, shared among all the graphics processing clusters, a set of memory controllers that connect to the VRAM located around the processor, and a PCIe interface for connecting to the CPU. When we zoom in to see a nanoscopic view of the integrated circuit, we find something very similar to what we saw in the CPU, with the transistors on the bottom and a labyrinth of multiple layers of metal wires above. All these structures are manufactured in multi-billion-dollar semiconductor fabrication plants, or fabs, but that's a topic for a whole different video. So let's move on. GPUs and CPUs are similar in many ways. However, GPUs have thousands of cores that are limited to basic arithmetic, whereas CPUs have only a handful of cores that perform far more complicated operations. Additionally, CPUs have branch prediction and deep pipelines that optimize the execution of code. Here's a quick example of what GPUs can do. Take this image comprised of 16 million pixels, each with RGB values for each pixel. A simple way to brighten the image is to add 20 to each of these numbers. A CPU has 10 cores and thus performs arithmetic 10 numbers at a time, whereas GPUs distribute the data to thousands of cores, thus performing magnitudes more parallel processing. Let's close this graphics card and talk briefly about the 3D model. Note that this is a slightly older model graphics card because we buy most of our hardware as non-functioning parts from eBay, and then, as shown earlier, we tear them down rather destructively in order to accurately model everything. Additionally, sometimes components shown aren't compatible, such as this motherboard that says DDR4, while the DRAM is DDR5. That said, modeling and animating everything to make it feel like you're actually inside a computer took us around 500 hours. And we would greatly appreciate it if you could take a few seconds to hit that like button, subscribe if you haven't already, type up a quick comment below, and share this video with someone who will enjoy it. The CPU communicates directly with the DRAM through memory channels running inside the motherboard. Inside each of these 8 DRAM chips is an integrated circuit composed of 32 memory banks, each 8,192 columns wide by 65,536 rows tall. The DRAM temporarily stores data using capacitors and transistors called 1T, 1C memory cells in 2D arrays that look like this. Data can be accessed within nanoseconds. However, among these 8 chips, only 16 gigabytes of data can be temporarily stored. SSDs, which permanently store data in 3D arrays called 3D NAND. This array is 100 to 200 layers tall, 32 to 64,000 columns wide, and 32 to 64,000 rows deep. Additionally, within a single SSD chip such as this one, are multiple 3D NAND arrays stacked one on top of the other. As a result, a single microchip can store terabytes of data. However, reading or writing data takes 50 or so microseconds, which is 3,000 times slower than DRAM. Zooming in on a single SSD memory cell, we find a charge trap which stores different levels of charge, allowing for 3 bits of data to be more permanently saved. Looking at the NVMe and SATA SSD, both have a few 3D NAND data storage chips, a DRAM chip for buffering and holding the data mapping table, and a controller chip. Let's move on and dissect the hard disk drive. Here we have a disk mounted to a spindle with a motor that rotates the disk at thousands of RPM. A read-write head moves across the disk in order to access a single track out of 500,000 other data tracks. Let's zoom in on the read-write head. The write head changes the direction of localized magnetic domains in a small layer on the disk, whereas the read head senses these changes in magnetic domains. This disk drive is even slower than the SSD, taking a few milliseconds to access, thus resulting in slower read and write times, but costing less per terabyte of storage. Thus far, we've covered all the hardware inside your computer. So, thanks for watching this far.